Hi, welcome back to our next session. The new topic is about the percentile, which is percentage rank. What we can write is denote as P of K. That means K percent of data is below the data value Pk. Right, so P of K represents a data value that is K percent of the data in the data set is below the value P of K. Right, that's the percentile, and we were focusing on the quartiles. Which denotes our Q1, Q2, and Q3, which is for a data set cut as 4 quarters, that's first, second, and the third quartile, which the first quartile is 25th percentile, that is 25% of data below our Q1. Right, that is the first quartile. Right, and second quartile simply is 50% of the data below our second quartile, which second quartile is 50th percentile. Right, 50th percentile, in other words, that covers that cuts right the middle of the data set, which in other words is the median. Right, that's our 50th percentile. Right, median, in other words, or when we explain more, right, that's 50% of data below our Q2. Right, then the third quartile is the 75th percentile. Of course, initially we have minimum, and after Q3 we have maximum value, right, to get an entire data set. That Q3 is 75%. Right, that means 75% of data below our Q3. Right, so that are special values of the quartiles. Right, if you have quarters, that means the quarters is cutted your $1 into 4 pieces. Right, each piece is a quarter. Then first quartile go to 25th%. Second quartile are 2 quarters that have 50 cents. Right, if you refer back to the money, which the second quartile is the 50th percentile of the data. That 50% of data is below our Q2, and so on, right, Q3. That is about the percentile, and especially we're going to cover the quartile. And for just roughly converting, right, the percentile could be more harder than that, but we just give an example in that easier way. Right, so we're given a data value. We're given a data set, we want to convert the percentile into the data value. Right? The percentile basically should represent using a data. That what we do is define certain things. First of all, n is number of data value. P of k, as we had said notation before, that's the case percentile. We use k to locate. Right, when we arrange the data, we're able to count it, right? Where the first one, second one, third one of the data set, what it is. Then what we are doing is convert the percentile to the location of the data. We need to use the locator. The L is the locator. Right, the locator gives the position of the data value. And how we calculate the locator is just multiply by n all times by the percent. Multiply n by k over 100. Right, that will convert the percentile into the locator to see which one the data will be. Right, that will be two cases. Well, when we get into the division, it may be the locator L to be a decimal, or maybe the locator L to be a whole number. Right, so what we do for steps. Right, the first step is to sort data. In the increasing order will be more beneficial since we are finding the 25th percentile or second quartile or the third quartile, which is to see in the view of from bit lower to higher of the data. Right, the second step is to compute or L. Which L is n times k over 100. Use that formula to compute L, right? Of course, we know the k, we of course have to know the n, right? Given the data itself. Then the third one is two cases. Right, so L may be a whole number, maybe not, right? So if L is a whole number, then we need to do more things. Take the mean of L and its next value. Right, if we get a decimal, no matter what it is, we will round up to the next whole number. Right, that's what we do for the finding the values. And at the end we have the interquartile range. Right, interquartile range is Q3 minus Q1. Right, that thing sometimes helps us to get to see what the outliers of the data set is. Sometimes people using 1.5 times of interquartile range below and above Q1 and Q3 to see that is the fence of the usual value. Right, before, we could use twice of the IQR. The book, of course, we're using is saying 1.5 times of interquartile range. Above and below the Q3 and Q1 are the outliers where they are. Right? If we have data value exceeding those fence, then they are outliers. And some other resource, I could say, well, twice of the IQR out of that range, above or below the Q1, Q3, right, could be the outlier. Some other books say, well, we use 95% confidence interval as the usual range of the mean and standard deviation of the data set as the usual value. We will touch those confidence interval in the later chapters, right, in the later chapter, which you will see. But well, that has too many things to deal with, right? And not agree together at all. So we simply could just omit it. That's also fine, right? Sometimes the outlier doesn't need to be shown on the data set very clearly what they are. So maybe asking us for interquartile range, that is fits, right? That is consists of what it's supposed to be. But the outliers, people using different things to do that, and depends on what you want to do, right? That outliers deciding will be differently. So we'll not talk about the outliers. But that is how we deal with the convert percentile to the data value. And what we deal with them is we use something called Box-Whisker Plot to graph our data set. The Box-Whisker Plot is a graph of data set using 5-number summary. Right, so what are 5-number summary? They are minimum, first quarter, median, third quarter, and the maximum. Right, those are 5-number summary of the data set, and we use that to graph our data set. Well, we'll see an example of how we find out those quartiles and how we draw the Box-Whisker plot. Right, that's our data set from 31, 36, 39, 43, 51, 53, 62, 63, 79, and 100. They are 10 numbers. Right, find five number summary and draw a Box-Whisker plot. Draw a Box-Whisker plot. Right, the data is well arranged, so it is, we don't need to arrange the data, right? It's well arranged. It's good enough. Then we have the minimum is the value of 31, right? That's clear. The Q1, the first quartile, is 25th percentile. Right? The Q1 first quartile is 25th percentile. So we get the K is 25. Locator is n times K over 100, which is 10 times 25. Is 2.5. And maybe I'll write it over there. Right, which means the P25 or the first quartile is the third data value. Right, since we get a decimal, we need to round it up. Right, that means our Q1 is the third data value, which we counted, the third one is our 39. Right, the Q1 is 39. And the second quartile is our median. You want to use the way to find the locator is fine. If you use the way to find the median is also okay. Right, if we use the locator, we can see that it's 10 times 50 over 100, which is equals 5. Therefore, Q2 is the average or the mean of the 5th and the 6th. Oh, we get the 5 as the locator. 1, 2, 3, 4, 5, 6. The middle will be the middle of the two. 5 plus 6. Not 5 plus 6. The 51 plus 53. We get the data value to be 52. Right, if we want to see how the data set goes, right, that we use the median as what we know, we cut off the first and last, the two simultaneously and left over the middle two values. And then to find the median, it will be the same average or the mean of the middle two values, right? They are same way. And then to find the Q3, that is 75th percentile, located similarly 10 times 75 over 100, which is 7.5. Round up Q3 is the eighth value. Right, so if I just keep consist, is the eighth value, data value. The eighth value comes backwards 10 9 8, that is our 63. And finally, the maximum of the data set is 100. And maybe you quite ask us to find the interquartile range. That the interquartile range is Q3 minus Q1, that's 63 minus 39, which is 24. Alright, that's our interquartile range. So the range from first quarter to third quarter, that's 24. Alright, so we sketch the minimum is 31, the maximum is 100. That Box-Whisker plot. We'll use those values from 30 how we draw the Box-Whisker plot is we use the middle three, Q1, Q2, and Q3 to build the boxes. And after that, we use minimum and maximum to connect the box. Oh, let's see. We get 39 as our first quartile. We draw a longer line saying that's Q1. Right, then our median is 52, which the same distance, right, to be same since we need to build a box, that's our Q2. And our third quartile is 63, that looks like it could be here, the third quartile. And we draw a rectangular box around it, and that's our interquartile range, what it is, right? From Q1 to our Q3, from 39 to our 63, and then our minimum is 31. We'll maybe draw a shorter line, right? Could draw a shorter line, right? Shorter than the box. That's our minimum. And then our maximum is at 100. We draw a vertical line at 100 to be our maximum. Then we use the whisker to connect them. To connect to the box. right, to show that the middle 50% is in the box, and we have the fence to the left, to the right, till the minimum maximum. Right, that's our Box-Whisker plot. Right. So that was what we have for the chapter 3, right? Then after chapter 3, we jump to chapter 10. Chapter 3 was about the numerical data and finding the mean, median, mode, the mid-range, even for the center, measure of center, and for measure of variation, we see first the range, then the variance and the standard deviation. In the middle short topic, we have seen the weighted mean, which is also important or a nice topic that can help us a little, right, in the real life. And what also we had seen was the find the mean and the variance and standard deviation for the grouped frequency distribution, which use the idea of frequency data, how we do that, and for the grouped data, we need to find the midpoint to do it, right? That's the frequency distribution. Then last thing, we have seen the percentile, quartile, and the Box-Whisker plot. And that's everything in chapter 3. Then for chapter 10, we had mentioned a little bit is about correlation and regression. Right, the chapter 10 is about correlation and regression. It used to analyze paired data. The important thing here is the data is paired data. We see some example in our chapter 2, right, at the end of chapter 2, that the data are in paired, which, an example, if you remember, right, the circumference of the arms and circumference of the waist, every point is a data from the same individual, right? That means it's paired data. If you get data from different individual, one's circumference with the other one's waist circumference, that is not a paired data. Paired data have to be coming from the same individual at least. Methods to determine whether a correlation between two variables exists. That's the way we will see, the methods to determine, for determining whether to determine the correlation between two variables exist. If we have a linear correlation, But if we have correlation and the correlation are linear, then we can identify an equation, right, of straight line that best fits the data. Of course, has different ways to do and the different ways of linear correlation to see if that exists or not, right? And we have a way to determine if that exists or not. Right? Then also, especially for the linear correlation, right? Also, maybe some data fits not the linear correlation, but some other type of the correlation that we are not discussing in our chapter. I will only discuss the linear correlations anyway. Alright, so we have seen a short example that the waist circumference and the arm circumference are somehow correlated. Then let's see the definition. Correlation. A correlation between two variables exists when the values of one variable are somehow associated with the values of other variable, or in other words, the one variable of test data value is depending in some way with the value of the other variable. The somehow associated, the somehow could be in a way of linear relation, could be exponentially related, or could be other way, like in a parabola way. Right? It could be. That's not necessary to be linear correlation. That's what to be clarified. And our course will focusing on only the part of linear correlation. The correlation between two variables is linear. And it also, in other words, the paired data results in a pattern that can be approximated the result of the pattern in the data, or the pattern can be approximated by a straight line. By that we have a linear correlation. Right, so we have correlations that, and we're focusing on the linear correlation in our chapter. So first of all, right, as we mentioned in the chapter before, we have to see how strong the linear correlation is. That, well, we say, well, to determine the correlation between two variables exists, right? First of all, have to be exist. Then, if they are strong, then we are able to, if they are strong, linearly correlated to be specified, right, then we are able to build a straight line, right, to going through the data. So first thing care about is measure the strength. Of the linear correlation. We have linear correlation coefficient. Of sample data, which is the lowercase r. It measures the strength of the linear correlation between paired value xy. Right, measure the strength of how strong it could be. Just before we see how we compute the R, let's see some pictures. Right, the first we have paired data. The paired x and y has positive correlation, which if we compute it, the R will be 0.851. Now we can see the graph that, well, even though we see a linear correlation, but looks like the point is a little more spread, right? Is a little more spread as the x going. So the R has the value of 0.851. We will see what the value can take. Right, then the next pattern. This pattern is more closer than the first graph we see. But that we can see as a line going downwards, which means if x is getting bigger or y is getting lower, that we get a negative correlation. And in the view of R, that is negative 0.965. Well, we see the correlation is negative in this case, but the value referred to the absolute value regardless the sign. The value of the number R is kind of bigger than whatever we found in our first graph. Right, then the third graph. Are full of random points. Right, this one cannot tell any correlation of the graph or of the points of the x and the y value. We see the random points in the third picture. That's if we compute that r equal to 0. And for a perfect line, r will be 1. And the other type of perfect line, r will be negative 1. This one is a perfect positive correlation. This one is negative perfect correlation. That we get r to be extreme value has 1 and negative 1. And the last case we'll see we don't see the linear pattern, right? But somehow we see another type of pattern. No linear correlation. The r is negative somehow 0.087. So it's very small, but somehow we can see there the pattern going increase, then go to decrease, which is follow a relationship of parabola. Right? But we cannot tell any linear relationship in between the measure of our x and y. So we simply cannot see, right? Cannot see the linear relationship. And we are not saying that that's no correlation. They have correlation, but just don't have the linear correlation. So the coefficient r here only can tell us about the linear correlation in between our paired x and y.